Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Maria Jump from Texas. She is one of Catherine McKinley's PhD students. A lot of you might have encountered her name before since she was heavily involved in the organizing of this year's PLDI. And she's to talk today about her explorations in the heap space.
So hi, like I said, I'm Maria. This is work that I've been doing with Catherine McKinley as part of my dissertation at UT Austin. Title of my talk today is Discovering Heap Anomalies in the Wild. So to get started, I want to set the stage for the work that I'm doing. Okay. I can see we're going to need to move this around. So essentially, my arguments are that applications are growing larger in size and in complexity. So because of their increasing size and complexity, they can no longer be developed by one guy sitting in his basement. They're developed by teams of developers that are sitting in different parts of a building or different parts of a room, depending upon the size of your company. One guy's working on one thing, another guy's working on another. They're creating software that's going to work together through an interface, right? But each developer or team of developers working only on a small part and truly understands only his small part of the application. The entire application is complex, and the person who understands the entire application doesn't exist anymore. It's really hard to understand how every piece of the application interacts with every other piece of the application, especially when you're talking about 500,000 lines of code. So they're all working really hard together. The developers are working hard. They're using all the tools available to them. And despite everything that they're doing, their programs are being released into the wild with bugs in them. We can't get rid of all of the bugs. So there's a couple of things that have been happening. Language trends are trying to make this easier by going to these languages that are object-oriented, that use automatic memory management and have an underlying runtime system. For example, C#, Java. These modern languages with managed runtime systems rock because they make the programmers easy to develop, they're faster, they're more reliable, they have less bugs in them. They're not bug-free, but they have less bugs. But they're also the wave of the future. Gartner reported that by 2010, 80% of all new software will be written in either Java or C#. So this is the way languages use seems to be going. And what it does is it provides us with an opportunity that we didn't have before, because now we have a managed runtime. And so what my research focus is on how do we exploit the managed runtime in such a way as to find the bugs that are in systems but in production. Once they're in the wild, the client has them now, they still have bugs, we want to be able to find them. So what we're doing is we're using techniques to dynamically detect the statistical or anomalous per object behavior, and because we're in a production system, they have to be very low overhead techniques, and we want very high accuracy because we want to be able to glean information from them. So the way I do this is I look at only the interesting objects. You have a problem, only some of the objects are contributing to your problem, so those are the ones we're going to look at. And I'm finding more interesting ways to summarize the properties to maintain this low overhead and high accuracy. Okay? So before I go any further, I want to talk about the space that I am actually working in, because this will just make the rest of the talk go smoothly, and everybody has to have this slide, right? So I'm implementing this in Jikes RVM. This is a Java and Java virtual machine that uses MMTK as its memory manager. There's specific things that come with the infrastructure that we'll talk about. I'm using 29 different benchmarks throughout different parts of this talk. Micro benchmarks, including the J. Olden suite, SpecJVM, DeCapo, SpecJBB 2000, and then as my real-world application, I'm using Eclipse. For a garbage collector, I'm using a generational garbage collector, GenMS, with a 4 meg bounded nursery, and for the performance, I'm doing the best to separate application time from the VM overhead by using second run methodology and replay compilation. And see, now we get to go and start anew. Wrong button. Okay, so I hope I've motivated that programs have bugs and that we need to find them. So next I'm going to talk about these two techniques that I've developed, dynamic object sampling, which was published in ISMM in 2004, and heap summarization, which was part of the work for POPL 2007, which some of you may have seen before because Catherine talked about it here a couple of weeks ago, like 3 or 4 weeks ago. And I'm going to talk about how we use these techniques for discovering heap anomalies, in particular unbounded heap growth and unstable heap arity. And then we'll conclude and we'll go to lunch. So what do we know? We know that objects have special properties. And what I mean by special properties is that objects have a specific lifetime. A particular object has an allocation site or an allocation context. It has a place where it was last used. It's used in a particular calling context. Which thread is using it? How is it connected to the rest of the heap? These are all characteristics that objects have that we want to know about objects, and we don't know them currently. So we also know that tracking these individual properties are very useful for debugging. There's a lot of tools out there that shadow every byte allocated. For example, Valgrind, LeakBot takes a whole copy of the entire heap to do analysis on the heap. We know that these are interesting things, that tracking individual properties is useful. So what we can do is we can use dynamic object sampling to help gather these fine-grained statistics about those objects that we are interested in. So how does dynamic object sampling work? Dynamic object sampling works by tagging objects with their special properties. And it does this by using 1 bit in the header to indicate that there's a tag present, and then adding a tag to the object. And we can track all kinds of things in here: allocation site or allocation context, /use site, its lifetime, what data structure it belongs to. We can put anything we want in there, and that tag can be as big or as small as we want it to be. So let's look at what that really means. So for example, here is a bump pointer allocator. And just to remind everybody what a bump pointer allocator does, is it takes a big chunk of memory, and as every object is allocated, it just bumps this pointer along until it hits a memory boundary, and then it asks for another chunk, and it does this again. It's a very fast allocator. It's the one used in all generational collectors in the nursery, and it does that because objects that are allocated together are often used together, so locality is good in the nursery, and it's very, 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 very fast. So when you add dynamic object sampling to this bump pointer, the bump pointer goes along as normal until there's an object that we care about. And then it sets the bit in the header, and it allocates a little bit more space for that object depending upon what we put in the tag. And if it's just a word, because we're encoding allocation context, fabulous. It's only a word that we're adding. If it's the entire allocation context from the time the program ended all in strings, then this is going to be really big. But our goal is to keep it small and still put useful information there. Allocation continues, and only the objects that we're interested in become tagged. And this reduces our overhead and keeps it small. So we also know that a tracing garbage collector like GenMS, right, provides this collection cycle provides us with an opportunity to gather these statistics about the live objects, because it goes and touches all the live objects and it decides whether or not they're alive. So have this opportunity to find out everything about the objects that are still in the heap. The objects that are dead, I don't care about. They're not going to be causing you a problem anymore because they're not being used by the program anymore. So the full heap object scan will completely summarize what's in the heap. Partial scans can be combined in intelligent ways if you know how to break the heap up. So if you know that only the nursery is being collected, you know what pointers come in from the mature space, you can make intelligent choices about how that goes, or if these two pieces and how they connect to each other, and you can have connectivity and at some point get a full heap summarization once you've collected all of the pieces and then merge them together. So by piggybacking on this object scan, we can find the survivors, and when we find a sample tag, which we know because it's the bit in the header, we now have the opportunity to do something special with this one object, but not with every object that we see. Okay, so what's the overhead of sampling? This graph is showing you the time overhead for adding those tags to all the objects, and then also looking at those tags during the garbage collection cycle. And on the y-axis, you can see it's the geometric mean of normalized total time across all of our benchmarks. On the x-axis is the relative size of the heap relative to the minimum that each benchmark could run. Each line has a bar. The bar represents the variation in the benchmarks. So the very top of the bar was the slowest benchmark. The very bottom of the bar is the fastest benchmark in our suite. So if you add a tag to every single object, because this is what a lot of people out there are saying, this is what I want to do, I'm interested in objects, so I'm just going to tag them all, I'm going to put it in the header instead of doing this this tag that we're doing, you're looking at an overhead, that's this purple line over here of every single object in the heap, and that overhead is like on average 7%. That's a lot of overhead. And it's because there's more memory being allocated, garbage collection's happening more frequently, you're looking at the tag, you're looking at the bit in the header. So there's all kinds of overhead there. If you take it and even sample a quarter of the objects in the heap, that's that green line right here, you still haven't reduced your overhead very much. But what's interesting is if you come down and look at these two lines, these are average, this is basically, the red line is 6% of objects and the blue line is 12% of objects. So now if you can look at only an eighth of the objects in specific, your overhead is like 3%. This is something that I think we can live with. Or at least we say that you can. So once we have this, we can gather all these statistics, but we need some way to summarize the statistics we gather. So we use a heap summarization graph to represent those statistics. And this is a new way of looking at summarizing the information of the heap in a very compact way. So here's the summary graph, what a summary graph looks like. Say you have a heap that looks like this, and this each object is a square. Each color represents the type of that object. And then, of course, there's references in between. In a summary graph, in a type summary graph, each type in the heap is going to have a corresponding node in the summary graph. Makes sense, right? Each edge between two types is going to have a corresponding edge in the graph. We're going to do more than just have the connectivity. We're going to keep track of how much there is. So we're going to keep track of the number of instances or the volume, depending upon your application and your needs, or both. In all my work, I keep track of both instance and volume for each type. But not only the types, but we're also going to keep track of these volumes along the edge, so that I know that there are two of the yellow objects being pointed to by one of these orange objects. Okay? So that also adds overhead. So how much overhead are we talking about here? So across our benchmarks, This graph is going to have one node per type, right? So we wanted to know how big this graph could get. And in this table, you can see two representative benchmarks from our suite, Jess and Eclipse. Eclipse is our largest benchmark. And you can see that on the top line here, in the system, the type system is aware of, on average, 1,747 types. That means that it thinks there's that many types in the system. But when we do a garbage collection and we build these graphs, only about 334 types exist on average at any given time in the heap. That means only about 19% of the types that the type system's aware of is alive at any given time, which we thought was very interesting. That made these graphs a lot smaller than we thought there would be.
That's 1747 number? That's the number of static types in the...
Yes.
I see.
Yes. And that's the benchmark and the virtual machine, because JIKES is a Java and Java virtual machine. So all of the virtual machine types also exist, right? And Eclipse has 3,365, of which the graphs only had 667 nodes.
And the meaning of a type existing is there exists an object of that type that exists?
Yes.
Okay.
There exists an object of that type live in the heap during that garbage collection cycle. Yep. The other interesting thing was, this is a graph. In theory, it has n squared nodes, right? But obviously, type systems are not as complex as graphs can be. And what we find is there's about 2.7 times as many edges in the graph as there are nodes in the graph, which makes this almost a linear relationship. Not almost, it is a linear relationship. So when you add all that together, you're talking about adding about 0.2% to your allocation overhead to allocate this graph at every garbage collection and keep it around for several cycles. Yes?
Make sure I understand. So you're saying that a large fraction of the types have no instances?
Yes.
That you observe, or that there just aren't? You observe every single object?
I observe every single object in the heap.
That's like on average, not ever.
No, but only a garbage collection time.
In every period of time.
Right.
Even on the max. So if you look at this number, 346 was on the maximum number. So this line here shows you that in Jess, there was 1744, 319 maximum.
Period of time.
No, across the entire run. Yeah.
What kind of workload are we talking about?
I'm not sure what you're asking. So I mean, Jess is a spec JVM benchmark.
Interactive applications.
That's right.
You're doing to cause these numbers.
That's right. So this particular run of Eclipse was its unit testing that's supposed to go and exercise all portions of Eclipse. And I'm not saying that the type at the beginning of the first garbage collection cycle is there at the last garbage collection cycle, right? That's not what I'm claiming here. I'm claiming here that at any given time, this percentage of types are alive in the heap. Now, if you change what you're doing in Eclipse and you go over here and start working on a different application, or you're now doing diffs instead of compilations, these objects are going to die. These objects are now alive, and now 20% of these types are in, not necessarily the same 20% that were alive at the beginning of the program.
Okay, so that's the trick, is that you're saying that there's sort of, but you're saying all the instances of these other types go away when you shift focus.
I mean, we didn't expect this, but that's what that's what we found.
So do you have a number for how many types were created during the run of the program in total?
No. Of course, I have all the results, so I could find that out. Yeah.
Do you have a sense for sort of a static approximation of the number of types, say, for Eclipse?
That Eclipse has in total? Yeah. This 3,365.
Oh, that's the number. I see.
Yeah.
That's the difference. Okay.
And that's Eclipse plus the virtual machine.
And that's the static number.
Yeah. That's the static number. Yeah.
What
percentage of those types are Eclipse versus the virtual machine?
So the virtual machine claims about a little over 1,600 of those.
Is that number constant across all of these
Yep,
workloads?
pretty much.
So like Jess actually only has 100.
Yep, pretty much. It's typical of a spec JVM benchmark. It's small.
So is the JIT compiler running
Yes.
while you're measuring this?
Yes.
Okay.
It is. So this is full run, adaptive compilation, everything going. And a lot of those types that are attributed by the RVM are part of the ones that are dying, right? Because the compilation objects are no longer needed once you have the compiled code. So a lot of those are dying off that you see in the beginning that you don't see in the end. But this was really interesting to us, and it showed how small the graphs could be, right? Yeah?
Okay, so just to understand, so that Jess, that 1744, that includes the virtual machine. So
Yes.
Jess itself only has about 150 types?
About that.
Okay.
Yeah. But Eclipse, obviously, the reason it's here is because it's the biggest and it has the most types. Yeah.
So for your counts on the live objects, does that proportion tend to hold up, that the number of actual types created also tend to be, those same percentages as to the total number of types available? As in, so of those 318 types, are most of those virtual machine types?
No, about half of those are virtual machine types, and the other half, about like 170 are virtual machine types that are alive, right?
Okay.
And that's virtual machine types and library types, right? Because I can't tell you whether this string was allocated by the VM or by, right? So there's a baseline there that is the VM, and this is just because I live in Jikes. So because we have increased the overhead, we've increased the time that we need, we are increasing the work, we've increased the runtime as well. And here's the same graph you saw before where the normalized geometric mean of the total time is on one axis, the relative heap size is on the x-axis, and this time you can actually see where each of the benchmarks were. But on average, we were talking about from 2 to 4% across the 17 benchmarks that we ran it on. Okay, so now we have two techniques. We have dynamic object sampling, and we have graph summarization. And so now we're going to apply these techniques to different problems. And we're going to start by looking at unbounded heap growth. So unbounded heap growth is an interesting problem because what is the problem? You have a data structure, it's growing every little bit every cycle, it's growing a lot every cycle, but it's getting bigger as the program continues to run. In the best case, no big deal, we increase the GC workload, your program runs, it terminates, everybody's happy. In the worst case, well, program runs for a really, really long time and your program runs out of resources. You get an out-of-memory exception on some allocation that's random in the heap on some data structure that has absolutely nothing to do with what's going on. Right? So, and some of you guys have probably seen this work before, but we're going to go through it pretty quickly. This unbounded heap growth is basically resulting from a program keeping around things that it doesn't need, whether the programmer is being conservative or whether he just doesn't think that maybe he should take things out of the hash map when he doesn't need them anymore, whatever. There's a data structure, one or maybe more than one, that is sitting there getting bigger and bigger through the course of the run. And this is what we call a memory leak in Java. Okay? So what we're doing essentially is dynamic memory leak detection. So here's an example. This is Eclipse. This is 3.1.2. It is a known bug in Eclipse. The bug number is on top. You can go look it up in the bug repository if you're interested. And what this graph shows is how is the heap usage over time. So on the y-axis is how many megabytes of memory the footprint of the application is. On the X-axis is time, and I measure this in megabytes of allocation rather than in T, because this is something that, how long did it take me to click? I don't care about that. I care more about through the course of the program. Eventually, as I was running this and testing this bug is for comparing two directory structures in two source trees. Memory use goes up, 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 and eventually it reaches the threshold and it goes, and we get to restart our application. So we looked at this and we looked at and we applied our summary graph to the problem. Actually, we developed the summary graph for this problem. In this case, this is the summary graph you just saw, right? In this case, we're tweaking the graph slightly. Instead of doing the standard graph that you see here, we are going to create a type points from graph. So what that means is that all of the edges in the graph are reversed. So instead of representing points to relationships, we know what type an object is pointing from. And this becomes important when we want to know the data structure, right? It's not a big deal for finding growth, but it's a big deal for finding the data structure that's responsible for that growth. So what we do is we take, yeah?
Did you already know the cause of that bug?
When I started this, no, I did not.
So this analysis was developed in absence of knowledge of the cause of the bug?
That's correct.
Okay.
And in fact, it was this analysis that resulted in the bug being fixed in Eclipse.
Okay.
Okay, so when you have a type points from graph from garbage collection I, say, and you look at the one from the next garbage collection, you can clearly see that there are types that are growing. They're getting bigger. You can clearly see that there are edges that are getting bigger. The volumes on the edges, the number of instances. We measured everything in volume for this work. If you compare it across multiple garbage collections, what you find is that some things are getting bigger and then, temporarily getting bigger, and some things are just getting bigger. And we wanted to find the things that are just getting bigger. The ones that go up a little bit, we don't care. It's the rest of them that we care about. So as you compare these across data structures, what we do is we take the types and we rank them by how much they're growing, so that when they go down, they're heavily penalized and the rank goes down really far, right? We decide that a type is a candidate being a candidate for the cause of the memory leak, when its rank achieves a threshold. And so we've now identified a type. So in this case, the yellow type is getting big, right? But that's not enough. We want to also know what is keeping that type alive. We want to know that it's from the blue object and not from this orange one over here, right? So we also rank the edges in the same way we rank all the types, and then we can take a slice through the graph. So a slice is defined as all the candidates plus all the edges whose ranks are greater than 0 that are connected from those. So it's basically, because it's points from, it's a reachability problem now along weighted edges in a graph. And this allows us to see beyond types that are not growing all the way up to the data structure. So let's see how we did. When we ran all our benchmarks on Quark, there's a small graph up here. I hope you can see it. Each benchmark is listed. The ones that have known memory leaks in them, because we can look at their heap occupancy graph and see the unbounded heap growth, are the ones in orange. So Jess, SpecJBB, and FOP. You can see the number of candidates that Quark identified as a leaking type. In the case of Jess, 1, SpecJBB had 4, FOP had 2. And when we go and analyze these programs, what we found is that FOP, while it does have a growing data structure and it does grow very aggressively, it is the design of the application to do that. And therefore, we can't do anything about it. But maybe they could redesign the application to not grow as fast, right? We let Apache know, because it isn't an Apache program, that existed. They said, oh yeah, that's the way it's supposed to be. Inspect JBB 2000, yes. It's been, so in Jess, it was pretty straightforward. Inspect JBB, it's a memory leak that has existed since Inspect JBB was released in 2000. And they've been trying to get rid of it. They've been trying to track it down. They never did. They never could. This work, in conjunction with some work done by some guys at IBM, was able to nail it down and fix it. Yeah. So then we also did Eclipse. And so let me show you the details of how Eclipse came out. So this is what came out of Eclipse. So let me just remind you, up on the corner there were 3,365 types static types in the system, of which 1,773 are types that belong to Eclipse and not to VM. On average, the number of nodes in the graph was 667, and the number of edges was 4,090. What you see on the screen is everything that came out of the slice in Eclipse. So it identified 6 types as candidates, and those are the ones that are in orange. And you can see that there is a relationship between these types. Clearly, if one's growing, they're all growing, right? But also, by following the ranks on the edges, we were able to pull in other data structures. And if you look at the edges and the ranks of the edges, the first thing you look at is this thing over here called resource input, my diff node. And clearly, if you're diffing 2 trees and you're running out of memory over and over again, and you're running out of memory, my diff node is probably one of the things that you want to really look at, right? But what this was able to show us is that my diff node was attached to a dialog box, which was being kept alive because of an incorrect ref count. So it wasn't being taken out of the list of active windows when you closed the window because the ref count was not being decremented. Once we added that decrement, 1 line of code, it went away. And I'll show you what it looked like in just a second here. But we also saw that this hash map was growing. And this hash map was growing, and when we looked inside the data structure, it had a mechanism to clean itself up. So it also used ref counts. Periodically, it was supposed to stop, iterate through the hash map, and take out everything that had a ref count of 0. That threshold was set so high, it was never triggered. As soon as we lowered the threshold, we have a much different view here. So this green line was after we fixed the mydiff node, but you can still see there is a very slight growth in the graph. The black line is once we also move that threshold down on the hash map. Now we've got almost a completely flat run. And that's what we want in our applications, right?
Is this this particular application, Eclipse, is that multi-threaded?
Yes, it is.
So was it difficult for you to fix the ref counting error?
Was it difficult to find it or to fix it?
Once you knew that there was a
No,
ref count?
it wasn't. I mean, it was literally adding 1 line.
You didn't have to, I mean, what if, with these ref counting errors is always tricky, right? Because somebody else might be trying to get a reference on it when you decrement it, and then things like that.
Right.
Maybe it's okay because it's garbage collected. Okay.
It's garbage collected. It makes it easier. Yeah. Finding it, whole nother story.
So fixing it was just decrementing the RC?
Yeah. So the green one was a 1-line addition to the program, and the black one was changing a number. But finding those, we won't talk about the time spent there. Okay, so this work called Quark, just realized it's the first time I've called it Quark, is basically a very low overhead technique using less than 5% space overhead and about 2% time overhead to find memory leaks in production systems. It accurately identifies the systematic heap growth So it's not trying to tell you that it's not supposed to be that way. It's just trying to tell you where your problem is and the data structure that contains that, and that's where it becomes useful. We believe that this is the first mechanism for detecting unbounded heap growth or memory leaks in a production system.
So how do you decide which objects are suspicious to start with?
They're growing.
So you start by
The
checking all objects
Yes.
and then you reduce it?
No, I check. The summary graph tells you that. So at this garbage collection, the volume of that type is bigger than it was before.
So you start by checking the garbage collections and then you start...
So during garbage collection, I construct a graph, right? The graph contains the volume of every type and the volume along every edge. And then I look to see how how it compares this time to last time, right? Or last couple of times, better yet. So from here through 2 cycles, right? That's what the rank is effectively doing. It's comparing this to this, but because it's a rank, it's getting bigger and bigger. The rank's getting higher and higher if it's continually growing. If it's not growing, it's basically 0 or near 0.
At that point you don't need a tag on the object.
No tags on the object. Yep.
And after that you add the tag, and what do you get from it?
We didn't actually have to add tags to this, but in the next work we're adding tags. Yeah.
So are people using Quark now outside of your group?
Right, so there's a couple of people who have integrated Quark. Azul Systems has integrated Quark into their VM, and I hear they're having mixed results just because they're not used to looking at it, and their applications are a lot larger than the ones I'm looking at. Lots of things going on all at the same time, very multi-threaded. But they are getting some positive feedback, and there's a version of Quark has been manipulated and modified and put into not an in-production system, but a dynamic analysis tool for EA. Okay, ready to shift gears? Okay, so unstable heap arity. This is the work that I'm currently working on, and these are very, very preliminary results. So I'll show you where we're going, and then hopefully you'll be able to read it in a paper very soon. So the inspiration for this work is HeapMD, which is a paper that was published in ASPLOS 2006. Published by Chilimbi's group here at Microsoft. And their work essentially was finding bugs in programs by using the observation that in spite of everything else that's going on in the heap, there are several properties of a heap graph that remain constant throughout the run of a program. So their paper reported 7 metrics. They all had to do with the arity of objects. Arity meaning how many in degrees, how many out degrees do objects have, right? So these were the 7 metrics that they used. In degree equal to 0, 1, 2, out degree equal to 0, 1, 2, in degree equal to out degree. They found that these metrics were relatively stable during correct runs of a program, but when a run went incorrectly, that these metrics went out of bounds of what they considered a normal range. Okay? So there was a larger rate of change than they were anticipating. So we took this work and we implemented it for Java because we were interested to see how it happened with the different way Java creates objects versus C and C++, which is where this work is. So in HeapMD and Java had very dismal results. We ran it across 7 benchmarks. 11 of them had no stable metrics, none whatsoever. A couple of them had 1 or 2. Some of them had every metric being stable. So what did that look like? This is the rate of change for all 7 metrics, all on the same graph, each one's being a different color here. For Jython. Jython is from the Decapo benchmark suite. It's approximately 180,000 lines of code. You can see its rate of change is very, very small. The rate of change of any of these metrics. On the y-axis, you can see the percentage rate of change. Very small. The scale of this graph is what they considered stable. Anything that went outside of this is when they considered it to be unstable. Okay? Those 11 other programs looked more like this. And in this graph, you'll notice that the rate of change, the scale on the y-axis, is 2 orders of magnitude bigger than on the last. And I still cannot contain the variation in these metrics, even by increasing it by 2 orders of magnitude. Very unstable, very all over the place. So we started looking at why and what we could do about it. And what we found was that when you map these types of statistics onto a summary graph, you have a very different problem. You're no longer looking at how stable are things across the entire heap, across the entire run of the program. Now you're mapping these statistics onto a type. And types actually have an expected in degree and an expected out degree. So what does that mean? Let me show you. Here's a linked list as implemented by Java Lang linked list. The blue nodes are the linked list nodes, and this is a private node class to the linked list. And hanging off of them are the data, is the data that you want to put in the linked list. So when you put this into a summary graph, you basically have 2 nodes. You have a node, an edge that points to the data, and you have a node that points to itself. So here, the linked list node has an expected in degree of 1 and expected out degree of 2. The data in 1 and 0. Does that make sense? So what about a binary tree? Same programming paradigm in Java-/Lang. Data's hanging off. The binary tree structures are in nodes. You end up with the same type of node in the graph, but now if you tease apart the fields into different edges in the graph, you can see that there is a left and a right in data. And the expected in degree and out degree here is different than it was back in the linked list, right? You have an in degree 2, out degree 3, data still stays the same. What's really interesting here is that the summary graph allows us to see these nodes. And these are what we call self-referring nodes. They have a link that goes like this in the graph, points to itself in the graph. And these are actually the nodes that we care about. Because if you think about all linked data structures, they all have a node backbone. Backbones all point to themselves. Right? Occasionally you'll find a data structure that says linked list node points to an array of linked list nodes that points to a linked list node. And we can capture that as well. So we started looking at these self-referring nodes, as I call them, and we wanted to know, well, how many of these exist? So here is all of the objects in the heap across all of our benchmarks. And this blue line, again, I'm in JIKES RVM, right? I'm going to assume that the JIKES RVM is correct. Maybe that's a bad assumption, but I'm going to make that assumption. The blue represents just the application objects. This is with JIT, adaptive compilation, and everything else, right? And you can see that a whole lot of objects are in the heap that belong to the VM.
I have a question.
Yes?
Why can't you do all this by just looking at the static type structure? That would tell you what the self-referencing references would be.
Say you have a linked list object that points to an array of object that points to a linked list. Your data hanging off of all of those list nodes, whether it's a binary tree or a linked list or
because they're
are of type object. They are not of type foo.
Okay.
right? They're not of type data, my data. They are of type object. Statically, this information doesn't exist. Sometimes it does. But in a library function, no, it doesn't. Not even with generic types does it exist. The generic type nodes all think they're objects, statically.
But if you look at the points to graph, then you know the concrete types.
But that's a dynamic.
No, you can look at the static points to graph. And then you'd obtain concrete types instead of declared types.
But I guess her point is that whatever static analysis you do is going to be very approximate. This way,
not necessarily in that example, for instance. And generics don't hurt concrete type analysis so much.
Trying to think of the example where you break. And I believe that it's probably where you are data node. My node derives off of my data node derives off of data node, which is what statically is in the graph.
I can still. I mean, suppose I rely on allocation size as my approximation. If I have a factory making a variety of objects, then that all, breaks essentially. So you can make an argument that it's imprecise, of course. But anyway, we can take it offline.
Okay. We should do that. Okay, so this is basically how the heap is made up, right? So the gray line is all of the objects in the heap. The blue one is just the application, not the VM, because I'm going to assume that the VM is correct. Of the application objects, the red line, the red bar, represents the self-referring nodes. And you get some of them over here that are really, really high. These are our micro benchmarks in JOLDEN, right? Triad adds a bunch of nodes to a tree. That's all it does, right? These benchmarks over here are the more interesting ones. These are spec. This is a spec JVM here. This is the DeCapo suite here. And they're ordered here, if you're wondering, by the number of types that are in the system. So this has the fewest number, Eclipse has the largest. It gets bigger as it goes. But looking at this, what we find is that about 15% max, well, not max, but yeah, about 15% are 18% maximum across the real programs on this side of the graph are self-referring nodes. This does not count the JIKES RVM. It does not count anything coming out of Java Lang. That means if you implement your program using Java Lang linked list, I'm not counting them here as self-referring, because I'm assuming that Java Lang linked list knows how to implement a linked list and it's correct. These are things that you've written in your code or they've written in their code that are self-referring. So clearly we have linked data structures still being created in our programs. But that 15% are the ones that I care about. When I examine the stability of each type compared to its expected arity, right? Not the arity across the heap anymore, but each type to its expected, what I get is a graph like this. Again, I have three colors, gray being every object in the heap, blue being just the application, and red being the self-referring. The self-referring are the ones that I really care about. And you can see that on average, they're pretty stable. Every now and then you get a bar that looks like this. That's because these programs don't have any self-referring objects. They do everything in arrays. Jess, bloat, compress. We see a similar result for out degree. So the stability of the out degree of objects compared to the expected out degree of objects is very, very stable. So this work is getting prepared to go to PLDI, submit to PLDI in a couple weeks. And so what we're doing is we've added dynamic object sampling to this. So now we've added tags to self-referring objects. The tag is encoding which data structure each object of that type belongs to. So now if you have two linked lists in your in your program, I can tell you which linked list it belongs to. So I can look at the stability of the end of these statistics in one data structure versus another. One's correct, one's not. And they get even more stable when you start doing that. And that's what this graph is representing here. This is the summary graph where each diamond represents a different data structure. So this is the self-referring node, which I didn't draw here, but it's the one that is going to show me which data structure is going to have a problem. Yeah.
So how do you separate data structures? Like by allocation sites, or by and if you do that, how do you do it?
By connectivity. So connectivity to a root.
Okay. But you don't know that at allocation time.
I don't know that at allocation time. I only know that at GC time. Because these graphs are being constructed at GC time. So I'm using reachability to do my GC, and I'm exploiting that.
So what do you use the tags for?
The tags are to distinguish one data structure from another. So if you have two linked lists in your program, I want to know that it's this linked list and not that linked list.
But you're populating that data structure at garbage collection time.
No, I'm analyzing it at garbage collection time.
Okay.
So the tags are being added to the object at allocation time, but the contents of the tag are being put there during GC time.
Okay. All right.
Sorry, I should make that clear, that distinction. All right, so GC time is actually writing in the tags to determine what type belongs to what data which instance belongs to what data structure, and thus which of the summary nodes it belongs in. So the other thing that Chilimbi didn't do that we think is very interesting is if you're doing a statistical analysis like this, how many errors have to exist before they show up in the graph? So these are measurements that are currently ongoing, and I don't have results for that. I'm sorry, I wanted to, but... And then, of course, can we find real bugs in real programs? So we're targeting Eclipse again, and there are several bugs that look like they are of this nature, and we're going to go after them. So hopefully I've convinced you that these are two techniques for detecting things that run with low overhead, high accuracy. Obviously I could do better at giving you more numbers for that. The dynamic object sampling and the heap summarization. We're basically exploiting the runtime, the garbage collection, and the runtime system for actual dynamically determine the types, for instance, to figure out these detailed characteristics of objects, and only the objects we care about. Low overhead, high accuracy is our goal always, and to provide mechanisms to debug software and production systems. Thanks.
I have a suggestion for future work. So a lot of the kind of work you do is trying to reverse engineer specifications.
Yep.
So how about the following revolutionary suggestion? Let the programmer specify what she wants to check, and then you try to check it as fast as possible. See, today what happens is that when programmers write assertions in their code, they have a very limited assertion language available to them. All they can refer to is variables in scope and basically simple expressions on them, right? I think one thing that you're trying to provide here is providing a very rich assertion language. You could refer to, for example, all the guys who are pointing to me. You could refer to all objects of a certain type. And if done stupidly, these kind of assertions have a very high performance penalty. But I think a lot of your contribution is how to make even complicated things like that fast. So I think that would be super nice.
That's a great suggestion. Thank you. All right then.
Questions? All right. Thanks.